Good morning, everybody. Welcome to the ECE Colloquium. Today we have our guest speaker, Professor Lalitha Sankar from the School of Electrical, Computer and Energy Engineering at the Arizona State University. Professor Lalitha Sankar has been at the School of ECE at Arizona State University since 2012. Prior to that, she was a research scholar in the Department of Electrical Engineering at Princeton, working with wind sports. She was also a Science and Technology Teaching and Research Fellow, supported by the Council of Science and Technology at Princeton. She did her PhD at Rutgers and has received many awards, including the Best Paper Award at IEEE Colloquium. She's also the Information Theory Society Distinguished Lecturer for 2020. It's a great pleasure to have her here. On a personal note, she's also been a great friend and a colleague at the Information Theory Society. So it's a great pleasure to have you here. We're looking forward to your talk on design of loss functions for robust learning.
Thank you, Shriram. And thanks everybody for attending this talk virtually. It's wonderful. So I'm going to get started. This talk is about a class of loss functions that we sort of stumbled on or designed through a different problem. And I'm going to get to the loss function itself through a little story. So walk with me as we, bear with me as we go along. So, broadly, the talk has 4 parts to it. I'll start with motivating the need for robustness in ML and then introduce this loss function. And this is a largely theory talk, so I'm going to actually tell you a way to look at performance of, expected loss, irrespective of the distribution of the data, through some kinds of tools that we have. So we're going to look at the optimization landscape of this for particular learning models. Right? And then I'll end this talk with some results. All right, so okay, this keeps happening, so I need to come back here. All right, so ML is now understood to be a method, machine learning, to use data to learn algorithms, right? And I'm gonna assume everybody here knows that. And the thing about using data to learn algorithms, either you can have very little data, or you can have very biased data, or your data could be subject to either noise or people actually tampering the data, right? So this has sort of been already shown, and there are these examples where you could be training classifiers to distinguish between different classes of animals or different kinds of objects or broadly different groups of things, and add a little bit of noise, which is not very evident to the naked eye. It looks very distributed across all the pixels. And then the panda is actually classified as a gibbon. Right? To me, it looks like a panda, and certainly gibbons have some similarity to this. But the problem was the panda itself started with very low confidence in the classifier. So when you're sitting at the boundary, I could just push you over to the other side of the boundary. Right? There's a lot of work emerging in this context. And one question to ask is, how do you make algorithms robust to this? So one way to do this is to actually, in the training, you allow the loss functions, so you allow your data to be tampered in a way that your learning is robust to changes in the data. So there's a lot of work recently by people at Berkeley and many other places, MIT and so on, where they are saying you can change the boundaries of these classifiers to accommodate for this. So one of the things we would like to do is, so this is for any particular loss function on the previous slide, can you actually use tunable loss functions that are inherently robust to outliers, right? So this is something this talk would broadly address. The other thing that's incredibly relevant right now as we speak, as we stand here, and our nation is getting literally burnt down outside, is that decisions are made every day in this country with data that could be biased. For example, Amazon tried to actually come up with a tool to predict which resumes to accept and whom to interview. And it turned out that maybe because they had very few samples, that they were just completely biased against picking women. Or maybe the humans were just not picking up women, right? There are all these examples of Google Translate where you could put she's a doctor, he's a nurse, and then it goes to Turkish, which is gender neutral, but when it comes back, it reflects that culture's biases of, having more males as doctors and more females as nurses, right? So how should algorithms respond to these kinds of things, especially when you know that these algorithms could very soon, much sooner than we expect, be making decisions, telling judges whom to give parole to and so on, right? So when we talk about fairness, there are these notions of how do you handle biases and how do you handle limited samples, okay? So there's some work we've done on societal biases where you say that you should suppress sensitive features in the data. There are other strategies for biases by resampling from the smaller data sets. One of the things we would like to understand, which I won't completely talk about because we're going to look at the theoretical aspects, but hopefully you'll get a sense for why alpha loss may be relevant in this context. Okay, so these are the kinds of broader picture questions that we would like to see this class of loss functions applied to. And if you're wondering where this loss function comes from, just look at this slide as a little story. This loss function comes from my ongoing and for a long time work that I've been doing on privacy, where I would like to understand information theoretic measures for privacy. And one of the things that has been a little bit of a problem when using information theoretic measures for privacy the pushback has been, you don't have operational meaning, you don't have adversarial models, and we started looking at that. So we created a loss functional perspective to a lot of information theoretic measures, and this is where this class of loss functions came about. So I'm sort of going to dive into my talk now, giving you a broader picture. So this is joint work with my PhD student, Tyler Seifert, who's in the audience. With a postdoc of mine who has now moved to a top mathematics school in Mexico, Mario Diaz, and Peter Kairuz at Google, my collaborator for a while now, and my fantastic colleague, an expert in learning theory, Gautam Dasarathi. Okay. So before I move forward, I want you to interrupt me at any point, either by raising your hand or hitting in the chat box, and if I don't see it, maybe Sriram, you can interrupt me. Okay. All right, so let's start with the definition of alpha loss. So we're in a setting where we want to maybe classify a feature or estimate something about it. I'm going to call y this random variable. That's the feature we want to estimate, right? So this loss function, and as I point my mouse towards, is working on probabilities. So you have a learning model and it spews out some probability. You take that probability and you raise it to this power where alpha lies between 0 and infinity. And even though this loss function is not defined right now for 1 and infinity, I'll make it clear in a moment. And you're going to take 1 minus this probability raised to this power, multiply it by this factor alpha over alpha minus 1, and you can take continuous extensions at alpha equals 1 and alpha equals infinity. So let's plug in specific values of alpha. When you plug in alpha equals half, if you look at this derivative for a moment, if you've taken your basic machine learning class with one of your awesome professors there, Kevin Jameson, this is really just the soft exponential loss. This is the weighting that you do when you use boosting or eta boost, right? Alpha equals 1, I get back something we're all familiar with, log loss. Okay, alpha equals infinity, I get 1 minus the probability of correctly guessing this, y as some little y. Okay, so 1 minus that, if you actually average it out, is the probability of error over all the samples. Okay, it's exactly what you would get if you put a 0-1 loss in there. Okay, so we call this the soft 0-1 loss. Let's look at a pictorial view of this. Right? So on the x-axis is the probability of y. On the y-axis is the loss values. Okay? So alpha equals infinity, you get the straight line, alpha becoming smaller and smaller. What you see is that for alpha equals 2, you're sort of capping off at about 2, right? And effectively what this loss function actually does is the weights on the low probability events, values for y, keep increasing as alpha becomes smaller and smaller. And you see log loss, it's convex. You see anything less than alpha equals 1, it's very convex. Okay, so you're actually going to put more weight on the outlier events, if you may call it that. Keep that in your head. Keep that intuition in your head as we go along. So let's apply alpha loss to a setting. What's our setting? Classification, the canonical problem in learning, right? So classification, we have features X, and we're looking at the supervised setting. You have a label Y, and we're going to use that supervised data to actually train an algorithm, okay? And the ultimate goal when you release the algorithm is to be able to predict Y, the label, from the features X that you've collected, right? So you could use any loss function. Our goal is to use alpha loss. Okay, so for any data XY that you have, the expected risk is if you knew the distribution of the data, you can plug it in and then plug the loss function in, and that's exactly the expression that you see there, right? You can ask yourself, what's the optimal strategy for this expected risk, right? That turns out to be what in information theory is called the tilted distribution. In this case, the alpha tilted distribution. What do I mean by the tilted distribution? Effectively, what we're doing here is we are taking the true posterior, P of Y given X, raising it to a power, and then normalizing it to make it a distribution, okay? And so promptly your question should be, okay, for alpha equals 1, what do I get? You actually get the true posterior. And you know that the optimal strategy under log loss, if you knew the distribution, is indeed the true posterior, right? And for alpha equals infinity, the optimal strategy is the map rule. You get your one best guess, and that's the guess that you pick, which has the most likelihood of occurring given what you've observed. Okay, so for alpha equals half, you get something like this, and for alpha equals 0, or alpha tends to 0, you actually get the uniform distribution. So this sort of gels with the intuition I just gave you that as you move, as alpha becomes larger and larger, you put less weight on the outliers, alpha becomes smaller and smaller, you put weight, almost equal weight on everything in the limit. So let's view that pictorially. I'll do that in a minute. If you plug in this optimal strategy, of course, all this assumes you know the distribution, and we'll come to the learning setting quickly, but it's good to have a theoretical basis for how to use this loss function, right? So if you knew the distribution, the optimal, the minimum risk as a result, the expected risk, turns out to be related to what's called the Arimoto conditional entropy. Okay. The Arimoto conditional entropy is sort of a generalization of the Shannon conditional entropy using Renier entropy measure. Okay, and it's defined like this. Okay, so pictorially, let's look at Y, the variable we want to learn, right? Y is binomial, so it has 20 values, and this is the true distribution of Y. Okay, condition on X, of course. All right, so if you were in the log loss setting, this is what, in an ideal world, if you had the distribution, you would estimate Y from XS. As alpha increases, what's actually happening is that the distribution is putting lower and lower weight on the low probability events. So it sort of becomes sharper and sharper, and the limit, you go to that point, right? So for alpha equals 100, you see how steep it becomes when the probability is on a log scale on the y-axis. On the other hand, when alpha is less than 1, alpha equals half, the exponential loss function, you've boosted up your outliers, okay? In the limit of doing that, you basically are ignoring the distribution of the data. You're agnostic to the distribution, and you weight everybody equally. That's in the limit alpha equals 0. Okay, so with this kind of a theoretical background, now let's ask the question, how do we apply alpha loss in the supervised learning section and for a specific learning model? But I'll pause for a minute if there are any questions. Okay, going right ahead. So let's broadly lay out the supervised learning setting. I'm going to walk you through things that some of you may already know. Bear with me. We'll work on the binary classification setting and also talk about the relevance of loss functions in this setting. What are the kinds of notions you need for a good loss function? Okay, so simple example, binary classification, canonical model for learning, right? So let's take MNIST, and MNIST is a data set of handwritten digits from 0 to 9, but let's just look at 1 and 7 because they look somewhat similar to each other, right? I don't know about you, I have kids, sometimes when they write, I can't distinguish between 1 and 7. All right, so here are your training samples, and you can just label all the 7s as -1 and the 1s as 1, right? So your X's are these images, right? And your Y's are how you've labeled this data, okay? Your goal is to learn from this labeled data set to be able to predict accurately when you get an unlabeled data point, okay? All right. So very broadly generalizing that, here's you have a feature space X, and X could be arbitrary, right? Could be in some d-dimensional space. And your label set, we're just looking at binary without any loss of generalization, +1, -1, right? So in the supervised setting, you get a bunch of samples, right? Or you have a sample n examples that you use, and you assume that they come from the same distribution on X and Y, right? So you train, and your goal is to learn H, a mapping from X to Y. That's your learning algorithm. And then you're going to evaluate your learning algorithm for some measure of performance, often called accuracy, in predicting how well you do when a new sample comes. Okay, all right. For which you don't have a label. All right, so the training is a way to make sure that you learn well on the data you have, but hopefully your algorithm generalizes to new data points that you see from the same distribution. Okay. All right, so the holy grail of machine learning theory too, has been to figure out what's the best hypothesis, we'll call this a hypothesis, right? The best learning model that you can learn, the simplest for the amount of samples you have that also optimizes accuracy, right? One measure that's very commonly and uniformly used across in all of learning theory is this notion of probability of error as an accuracy metric. So it's the average number of errors you make over all the data points, right? And for this particular H that you've picked. And for this measure, which is really the risk, if you looked at this I as the indicator function, this loss underlying it is just the 0-1 loss. You get a penalty of 1 for making an error, you get no penalty for not making an error, right? So the Bayes optimal strategy then is simply to take the true posterior, subtract half from it, and take the sign of that, and that's the best classifier you can have. Okay. If you knew the distribution, of course. Okay. And you're taking the true posterior for y equals 1. You know, this is a Bernoulli random variable. You get the other one immediately from eta. Okay. All right. So, so then the Bayes risk is just the minimum probability of error when you plug in this optimal strategy, H star. Okay. All right. But we all know that when you have a finite number of samples, and in an empirical setting, you do not have the distribution at hand. You average over your data points to estimate your accuracy, right? Computing this is NP hard. So if you go back to boosting as an example, instead of computing this, which is what they want to do, they upper bound this by the exponential loss. In a lot of practical examples, you use the hinge loss, you use log loss, you use a bunch of other loss functions, right? And it's because optimizing the 0-1 loss is NP hard, and there's, at least for the last 10 or 15 years, there's been much interest in having surrogate loss functions with desirable properties. Okay, there's a lot of work in this area, so we're certainly not new to this. And we're certainly going to talk about a few properties with respect to our loss functions. All right, so before I go any further, I have to set up this notion of classification a little bit more precisely, right? So classification is a way of taking your features X and mapping it to some number that allows you in turn to predict the label. So there are two ways to do that. You can map your features through your classification function to the set of all reals. And from the reals, you can just take its sign and then say that's your binary outcome. Okay? So the combination of the classification function and the sign-based saturation, if you want, is your entire learning algorithm H. Okay? Or your hypothesis H. Another way to do it is absolutely obvious, right? You don't have to go to the set of reals. It's just as infinitely infinite as the set of from 0 to 1. You just map to 0 to 1. So you're estimating sort of a distribution, a likelihood, and that allows you to estimate the true posterior in some sense from the data. Then you subtract half from it, take the sign, and that's also a hypothesis. Okay, so there are two ways to do this. The first one is called classification function. The second one is called soft classify, right? And you may wonder, how do you go between these two? It's not very hard to do, right? I'll tell you about it in a minute. The best F or G, so effectively, once you know F or G, you know how to take the sign and you can actually classify. You can give me a hard classification result. The choice of F and G, of course, depend on the loss function. That's what you're learning. You want to pick the best F or G that minimizes some measure, depending on your loss function, over all the samples. Okay? All right, so F and G are obviously related. You just put a sigmoid, and that sort of saturates your values between 0 and 1. You take an inverse sigmoid, you can go over the entire range. Okay? All right, so there's a direct one-to-one mapping between classification functions and soft classifiers. Why do I bring this up? Alpha loss operates on probabilities. Therefore, it operates on the 0-1 space. By definition, you need a soft classifier. A lot of properties for classification are based on classification functions. So I'm going to go back and forth. I'm going to set up alpha loss as a soft classifier. Just use a sigmoid, put it in the classification function setting, an inverse sigmoid in this case. And then you can talk about properties, okay, particularly classification calibrator. So one of the ways that we talk about good loss functions, good surrogate loss functions, is this notion of margin-based loss functions. Okay. So what is that? It says, look, you have data points X and Y, right? And you have this function F. Let's put them together. F takes X and predicts something, and Y is the ground truth. Okay. And so margin-based loss functions are these L tildes that operate on the product of Y and F of X. So why is this interesting? In binary, it's actually very simple. If F of X agrees in sign, remember it's classification function, and you're going to take the sign of it to predict your final label, with the true label, then you're right, irrespective of whether Y is +1 or -1. And right? And if it doesn't, then you've incorrectly classified. And for the 0-1 loss, with respect to the margin, everything that's negative has a weight of 1. Everything that's positive has a weight of 0. So that's what's plotted here, right? We aspire for the 0-1 loss. It's very hard to do in practice. We've used hinge loss, which looks like this. We've used exponential loss, which looks like this. And we also use logistic loss, which looks like this. Okay? And if you look at all these loss functions, they behave differently when the margin is negative. Instead of weighting them less, they sort of tend to go up, either linearly or logarithmically or exponentially. Okay? All right. So alpha loss is going to actually straddle and allow you to tune between many of these loss functions, particularly logistic and exponential. Right? So it allows you to approach 0-1 loss, as we'll see in a minute. So margin-based loss functions are very useful in analysis, especially in binary, because they synthesize both the label and your classification in one form. Okay, so as I told you before, alpha loss acts on soft classifiers, right? It needs a probability estimate. That's what my soft classifier gives. Okay, and So my soft classifier is directly mapping, and what it gives as an output is the probability of y equals 1 without loss of generality, okay? Given any observation or feature x. So transform this to a classification function, you just use the same one. Okay, spread it out. Okay.
Also, there was a question on chat on just the alpha loss function. So the question from John says, is there something special about raising to a power, or would any parameterizable set of monotonic functions work? So is there something unique about the alpha loss?
That's a very good question. I think for probabilities, raising to a power gives you these properties of either weighting the outliers more or weighting the outliers less. Would this work by scaling or other kinds? I don't think so, but honestly, somebody else asked me this question in a different context of whether distance-based loss functions could also be scaled like this, and we think so, but I couldn't answer that question beyond that more precisely. That's a great question, though. I'll give it some thought.
But you do have some of the operational interpretation from the privacy, so that the alpha losses show up as the right answer.
Right.
Do they translate to some property here in the learning context?
So, can I come back to this question at the end? Because I want to make a connection, but I want to go up on my slides and I don't want to do it right now.
Sure.
I'll come back to this at the end of the talk. I hope you'll ask me this question. Great question. Thank you so much. So coming back to where I was, so here's my margin-based form of alpha loss. And what is Z? Z is now the product of the label and the classification function. Okay. All right. So, and that's my probability, and I raise it to my power and then scale it like this. And kaboom, you put in different alphas, you get these. You get the sigmoid version of the 0-1 loss, you get the logistic function, and then you get the logistic loss and the exponential loss. Okay. Here's a visualization I want to keep in your head. I want you to keep in your head as we go along, right? So if you look at the blue curve, that's alpha equals half, and you see as a function of the margin on the x-axis, how steeply it weights the errors or the outliers, the ones for which you've made a mistake on your learning algorithm. As you go lower and as you increase alpha, that weighting actually reduces. And the limit in the 0-1 loss, you get this. Okay, so when you look at this loss function, as a function of the margin, you see that it's very convex for alpha less than or equal to 1, and it becomes quasi-convex for alpha greater than 1. Okay, there's some work by Montanari and his colleagues that non-convex losses are better for deep neural networks. So this it sort of builds the intuition that maybe we can go beyond log loss to get towards 0-1 loss, and by tuning alpha. And some of the things I'll tell you in this talk is you really don't need to tune alpha very large. You'll see all that. So I'm going to make all this intuition somewhat clear in the next few slides. Just stop with one property of this loss function is a known property for good surrogate loss functions is this notion of classification calibrated. And what that means is that with respect to the margin, whatever surrogate loss function you take, it sort of breaks up the region in a similar way to what the Bayes optimal system predictor would do. Okay, in the interest of time, I'm going to let this be. So such good loss functions are called classification calibrated, and we can actually prove that the entire family of alpha loss functions is classification calibrated. It was already proved for alpha equals 1 for log loss. It's known for 0-1 loss. Now we just straddled everything in between and just covered the whole range. Okay, all right. Now let's zoom in on a particular learning model, which I call the logistic model. I'll make it clear in a minute. And let's understand is it really easy if I tune alpha away from 1? I know things work well for log loss in practice. I don't know theoretical properties, and this will allow you to learn that. But if you move away from 1, either below or above, how hard does it become to optimize? Okay. So what does logistic model even mean? First, we assume that you have a d-dimensional feature space, all right? Without loss of generality, it's in a unit cube, or in a ball of radius, in a sphere of radius 1. And our parameters, theta, are also, of course, in a d-dimensional space, but in a sphere of radius r, okay? So what's our model? Our model basically takes this d-dimensional vector and takes its inner product with our model parameters theta, and then applies a sigmoid to it, because the sigmoid then gives me the probability. Okay. So I'm sure most of you have heard of linear regression, where you put a line across a bunch of points, and logistic regression is where you actually put a sigmoid across a bunch of points. Logistic regression is different from the logistic model in the following sense. Logistic regression, as used in machine learning parlance, is where you take the logistic model and you apply log loss as the loss function. And that's not what we're going to do. We're going to take the logistic model and apply the entire family of alpha loss functions. Okay? All right, so here's our setting, visually seen here. X1 through XD are my d-dimensional feature values. They come in, I multiply it by its corresponding weights, I take a sum, and then I do a sigmoid activation. I take that and plug it into my loss function. So let's pick some value of alpha, right? We're going to actually, alpha is obviously a hyperparameter in practice. And I'm going to tell you it's not very hard to tune over it, right? Okay, so if you plug this in, you plug in this logistic model, you get this loss function. Effectively, that's really equivalent to, you take your probability, which is your g theta. This is now written in a margin-based form. And then you raise it to this power and you expand it, you get this, right? For alpha equals 1, you basically recover cross entropy. And the expected risk is, of course, if you knew the true distribution, it would be over all the samples in the distribution. Okay, all right. So what I'm going to walk you through in the next half of the talk is really how does the optimization landscape change as you change alpha, okay, of this risk, of the expected risk. All right, so here's a visualization for a data set, which is very simple, a synthetic toy data set, right? X is conditionally Gaussian, conditioned on Y, taking binary values +1, -1. And so it's conditionally Gaussian for each of those values. And here are the parameters there. And this is a two-dimensional, X is a vector in a two-dimensional space. So that's why you have theta1 and theta2 as your model parameters. When alpha is slightly less than 1, this is what the risk, the expected risk looks like. So, it's Gaussian, right? You can compute this precisely. And as I increase alpha, what you see happening is that, here you can clearly see it's convex, right? It still looks convex here for alpha equals 2. And as I increase alpha, what you see is that there's some flattening of this landscape. In fact, if you look at the y-axis, you go from very large values, the range, to smaller and smaller ranges, and you start seeing little frills or ruffles, and there's still a point where you sort of have a well in the middle. Okay? We're going to quantify these things precisely using this notion of strictly local quasi-convexity, introduced by Hassan and his colleagues at Princeton. Hassan. Okay, so here's our first theorem. What we can actually prove for the logistic model is that for alpha less than or equal to 1, the expected risk is actually convex. Okay, even more so, it's actually strongly convex in the model parameters theta, okay, where the strong convexity parameter, often called M, is this value. And capital lambda is defined right here. It's a function of the, the radius r of your parameter space and the sigmoid, and of course alpha. Okay. And lambda i's, the little lambda i's, are the eigenvalues of sigma, where sigma is the autocorrelation matrix of X, right? And it's assumed to be positive definite. Okay. So how do we prove this? So anytime you're talking about strong convexity, you would start with the Hessian of the expected risk, and that's exactly what we do. And assuming that you can interchange the derivative and the averaging for well-behaved distributions, you get this. And for the logistic model with some algebra, you can actually write it in this form. Okay. And of course, by definition, this matrix is positive semi-definite, and we're going to assume that's actually positive definite. And in that the smallest eigenvalue is non-negative, which allows us to do this. So just like in the scalar setting, you know that something is convex when the second derivative is positive, and it's strongly convex if you can lower bound that, or if you can bound that. And in the general setting, the Hessian, you have to lower bound the minimum eigenvalue of the Hessian. And that's exactly, that's what we can do by assuming something about the distribution of the data. So we'll pause here for a minute to give you some time to ask me a question. So this is certainly assuming that my distribution is not in some lower dimensional space, in that it's fully expressible in this space, right? So keep this in mind. For alpha less than or equal to 1, I actually have an average risk, the population risk, which is strongly convex. Okay, all right. So what if you increase alpha? Okay, so what we obviously need is a tool. And the next thing to do beyond convexity, one of the reasons learning theory is difficult to explain neural networks, and we're trying to do that now, is this issue of convexity or the loss of it. The first step away from convexity is quasi-convexity, or one step away from it, right? So Hassan et al., about 5 years back, introduced a definition for quasi-convexity, and they actually called it strict local quasi-convexity, and this is as follows. Okay, you have theta naught, which is your minimum, and you are at some point theta, and you need two constants, kappa and epsilon. They're non-negative. So a function f of theta, right, and it maps from the d-dimensional space, obviously, to the reals, is epsilon kappa theta naught, with respect to that minimum point, strictly locally quasi-convex, if one of the following apply. The first requirement is either you're within epsilon of this minimum theta naught, which is going to be here, by the way, or, so if you're within epsilon, even if you're here, you're almost at the minimum is the idea. So you could have some frills near your minimum, right? Or ruffles, or whatever you want to call it. Or if you're outside this plane, okay, your gradient is such that, right? So the inner product of your gradient and all points that are within a ball of radius, epsilon over kappa, about theta naught, that inner product is pointing in the direction of descent. Okay, it's negative. All right. So the gradient is such that you're going to point in the direction of descent towards theta naught. Okay, so this is clearly a definition. Some people don't like these kinds of definitions, so I apologize for that, but this is a way of quantifying a local optimum property, and this is what we'll use. The things we'll actually do is we will rewrite this in an equivalent fashion that allows us to prove things for alpha loss. And that itself is a property of independent interest. Okay. All right, so here's another way of visualizing this. Here is this we've done again for the two-dimensional Gaussian mixture model. Here's your theta 1 and theta 2 parameters. Here's your theta naught, it's your minimum. We've plotted this for alpha equals 1. You can see the clear convexity. I can pick some epsilon, right, plane. And then for points above it, you will satisfy this condition. You sort of know that. You're actually strongly convex. So trust me, I'll just prove now as a corollary that you're going to be SLQC. Okay, all right. So it turns out Hazan et al. Also included this, that if your function f is G Lipschitz, right, as a function of the model parameter is theta, and strictly quasi-convex, then your kappa becomes that G. Okay? The SLQC parameter is such that for some epsilon, kappa is G, and then you have this theta. So one of the things Hassan et al. Also did was to say, under S sub QC, what kind of guarantees can I give if I use, say, normalized gradient descent? Okay. They also did it for stochastic normalized gradient descent. I'm just going to focus on normalized gradient descent. So what is normalized gradient descent? You literally, as the name says, you're using the gradient, but you're normalizing it by its length. So you're literally taking the same step every time. And eta is your radius, epsilon over kappa. Okay, so if you choose eta is epsilon over kappa, eta is your learning rate, then you can get below that epsilon plane as long as you run your algorithm for at least this many iterations t, and you can see that the iterations are inversely proportional to the radius of this ball, epsilon over kappa. Okay, so obviously your starting point theta 1 matters. How far you're from it, the further you are in distance, L2 distance, it's going to take longer. The smaller the radius of the ball, it's still going to take you longer because that cone has become narrower and narrower. Okay? Any questions? Okay. So right off the bat, for alpha less than or equal to 1, since I told you that my, under the logistic model, my expected risk is actually strongly convex, here's my corollary. For alpha less than or equal to 1, for sigma greater than 0, that's my only requirement I have on the distribution of the data, then my alpha risk, that's my expected risk, R alpha, is SLQC. For some epsilon, where kappa is the CR alpha, it's actually just the Lipschitz parameter of R alpha with respect to alpha. Okay? With respect to theta, I'm sorry. All right. Okay. All right. So here's what we have visually. That, of course, I'm strongly convex. Therefore, I am quasi-convex. That's all is there in that proof. And therefore, I can actually quantify the Lipschianity of it. Okay, with respect to theta, and then I just plug that in. So all I'm telling you, and this makes sense, exponential loss, very convex. Log loss, very convex, right? So I just captured that here, and I told you how many iterations it's going to take if you use normalized gradient descent. So what I want to do is I want to use this property now to tell you something for alpha greater than 1. Okay, I just actually literally walked you through this proof. So this is where we are. But there's a very interesting thing before I go to alpha greater than 1 that I want you to understand. You may think, oh yeah, it's so convex. It's great to operate in this regime. Why don't we just keep alpha less than 1 all the time? It turns out this Lipschitz CR alpha, the Lipschitz constant, actually blows up when alpha becomes smaller and smaller and smaller. Okay, so you get very convex, but if you're sitting further away from your optimum point, it's going to take you a very, very large number. Remember your learning rate, it depends on epsilon over kappa, right? And kappa is CR alpha. So this learning rate goes to 0. It's going to take you infinitely long to converge as you make alpha smaller. So it might be tempting to think in the weak learning setting, alpha equals half is what we use exponential. And if you had really good data set, maybe you could tweak it less than half. You can, but trust me, your number of iterations are really going to blow up. Okay. And in other settings too, you have an imbalance in your data. You want to boost up your outliers. You should use alpha less than 1. How far down? SLQC tells you it'll be unwise to make it very, very small because it's going to take you a lot of iterations. Okay. So the good news is then you don't have to tweak alpha very much below 1, and you can still get some gains by boosting those outliers. Okay. All right. So that's exactly what we say. In our experiments with deep neural networks, we haven't taken alpha less than 0.8. We've also done some work on boosting, and I'll talk about it at the very end. Okay. Yeah. So what if we increase alpha? Now I want to give you some theoretical properties. I'm going to start off with a proof. I think I have about 15 minutes, and I think I can be done in that time, but just keep interrupting me, please, if you have questions. So our first result is an equivalent way of writing SLQC. Okay, so if you are above that epsilon plane, if you're below the epsilon plane, you know what, fine, great, you started at a random point, that's pretty close to your minimum, you're done. Okay, success story. But most of the times we're not. Most of the times you're above that epsilon plane, depending on how you choose epsilon. And then you have to, that's why you have to quantify these SLQC parameters very precisely, right? So if you're above that epsilon plane, the way SLQC is defined is that your, the inner product of the negative of your gradient and some point theta prime with respect to, the point you're at theta, right? Some point theta prime, which is within this ball of radius about theta naught, right? Is such that that inner product is greater than or equal to 0. Either you can write it as the inner product of the gradient itself is less than or equal to 0. I took the negative sign inside. Now this is greater than or equal to 0. It's exactly equivalent to what I wrote before. So the problem with this is this requires you to test this with every point inside this ball, the way this definition is written. So what we're going to do is write in an equivalent fashion, okay, that says that this, if you can prove that this is lower bounded by your radius rho and your gradient at the point you're at, and then these are exactly equivalent. So I'm not going to walk you through this proof. It's a very cute little geometric proof using very simple geometric inequalities. But we're going to use this to now tell you how do the SLQC parameters change if you start at a point where you are SLQC. So you know that if you use the logistic model, up to alpha equals 1 from 0, you're SLQC. So which means, you start at some point, you're going to go towards the minimum with some guarantees, these epsilon guarantees. So you start at this point. Can I actually use this point to sort of bootstrap and give guarantees for alpha greater than 1? Okay, so that's what we want to do. And so we will use this equivalent form of SLQC definition now to do this. Okay, so here's our theorem. This is how the SLQC parameters evolve as alpha increases. So let's start at an alpha naught that is at least 1. Okay, and that works, right? Alpha naught equals 1, I'm SLQC, so I can start there, right? And for this alpha naught, I have epsilon naught and kappa naught as my SLQC parameters. That's my plane, and epsilon naught over kappa naught is the radius, about a point theta naught. And keep in mind, I can only give you guarantees with respect to this minimum theta naught, okay, that I started with. So if our alpha naught is SLQC with these parameters, then as long as I move alpha over no more than alpha naught plus this quantity, as long as alpha is greater than alpha naught, then this R alpha is SLQC with corresponding epsilon and kappa parameters given by epsilon plane goes up by this amount, okay, sort of linearly proportional to alpha minus alpha naught, and there's this Lipschitz constant, okay, which I'll talk about in a minute, and the radius shrinks from alpha epsilon naught over kappa naught in the following fashion. So this I and J are all constants that depend on R, theta naught, epsilon naught, alpha naught, and kappa naught. Okay. So let's parse this theorem before we go through the proof. Okay. All right. So I'm going to provide you some visuals, right? This holds for all alpha. So the way this proof sketch goes is as follows. I start with, say, alpha equals 1, and then I have this theta naught, and then this ball of radius, so, and then I have an epsilon naught over kappa naught radius about theta naught, right? And here is my epsilon plane. This is the epsilon naught plane, okay? All right, so the way we're going to prove this is that for epsilon at least, what we will use is the fact that R alpha is actually Lipschitz in alpha from 1 to infinity, okay? And that Lipschitz parameter is LR. It's of the order of R squared, which can worry some people, but we'll come back to that later, right? And it's very simple. What I do is this is the basic idea of the proof sketch. You just take R alpha and R alpha naught, R alpha of theta and R alpha, yeah. So you're computing R alpha of theta with respect to R alpha of theta naught itself. Okay, so you add and subtract and you use the fact that this is Lipschitz and that at alpha naught, you know the epsilon plane, kaboom, you get. So if you go from this visual to this visual, I move my plane up. Okay, so go back here, right. So you may think that's okay, but what this is telling you is that as alpha increases, you're going to allow for more frills underneath. The plane goes up, right? And this also means for more points above the plane, you have to give guarantees now. Okay, all right. So that was for epsilon. And the slightly harder proof is now, if I was already sitting, this part of the proof that I just gave you was all, if you were under the plane, are you still SLQC? Under the original plane, turns out you are, right? The plane goes up a little bit. But if you are outside that plane, to start off with, what happens? Okay, so I do not have all the time to go through the proof sketch, but I'm going to give you some sense of how we do this. What do we need to do? We need to show, we're going to use this fact, but what we need to show is the following. We need to show this last thing on the slide, which is that above this plane, all these points also satisfy SLQC in the following sense. Epsilon over kappa is the new radius, and for all those points, the gradient is such that you can bound this inner product, lower bound this inner product by the product of this radius and the gradient. Okay. I was hoping I would have some time for this proof. I'm just going to very briefly walk you through this proof, okay? So you're sitting at points outside the original plane, keep that in mind, outside above epsilon naught, okay? And what we do is we start with this form and we work towards this lower bound. And it's just using a bunch of triangle inequalities and intelligently. And also we need to bound, and this is where that range of alpha is coming from with respect to alpha naught that I put out in the theorem. You need to lower bound the derivative, the gradient at R alpha naught, okay? All right, and we continue to use the fact that it's Lipschitz in alpha inverse too. Okay, so you got an LR, which is Lipschitz in alpha, and you have a JR, which is Lipschitz in alpha inverse. Okay, and JR is about this order. R sigma R. Okay. All right. So, so this is why this definition comes about, where we are sort of taking the infimum of this, and you plug it in, you sort of get a product of this times this quantity, and if you pull out this, this is your original radius, you still need to put the radius in terms of the new radius, and you have to do a little bit of manipulation, and you can do that, and then you get this new radius being a function of the old radius in the following form. Okay. All right. So the real idea is the takeaways, right? So you know that if the radius becomes smaller and smaller, you need more and more iterations. Remember, the radius is epsilon over kappa. So T is inversely proportional to the radius. So clearly for alpha greater than 1, the SLQC parameters deteriorate. Okay. All right. Maybe there's a question. I see something in the chat box.
No, just a few more minutes and then we can take questions.
Okay. In that, Sudipto, indeed, you lose convexity, but the whole point of talking about SLQC was to say that you can quantify this convexity in some manner. I hope you come away convinced with that, right? And the interesting thing about all this is, at least with the logistic model, what we've done is we've told you how hard it is to go from, say, log loss all the way to 0-1 loss. How much harder does it get, even if you had a loss function like alpha loss, to do that? How hard does it get in terms of convergence, in terms of iterations? Okay. All right. And so this alpha, you know, so remember, you could only, if you were SLQC up to this range, you become SLQC in another range, but the width of that range obviously depends on the distribution of the data, but you can continually bootstrap. If you're SLQC here, you can bootstrap to here, and so on and so forth. Okay. All right. In the absolute interest of time, we have a generalization based on Rademacher complexity that actually tells you how well does alpha loss do with respect to your ideal 0-1 loss. All right, and it tells you that this is generalization, right? This is bounded by LR, which is my Lipschitz, okay, with respect to alpha, and it's over, so it's, you know, sort of 1 over alpha, right? So if alpha is 10, you sort of see you're within, you know, 0.1 of accuracy from your 0-1 accuracy. Okay. And in practice, we often see that this is much, much better. For example, you take this Gaussian mixture, you see alpha equals 4, and literally this is theoretically alpha equals infinity. We were able to plot it out because we have a closed form expression. You can eyeball, you can see some differences, but not too much in the landscape. All right, so in this case, the radius is 100. All right, so concluding, what I actually want to convince you is that alpha loss is a way for us to do, not just be hyperfixated on just log loss because it seems easy and convex and easy to work with. You can actually tweak a little bit over and below, and you don't need to go too far. You make alpha too small, you have exploding gradients, right? Too small, not a good fit. Too large, not a good fit, right? So there's actually a little nice little Goldilocks range, which my student came up with this term. It's very cute. And also due to the saturation, as I pointed out from our Rademacher results, you don't need to go very far. And this is what we've been doing. So I'm going to take the last few minutes. I'm going to skip the slide, take the last few minutes to tell you about experiments. Okay. All right, so recall what we want to test is, are you robust to noise, which are like outliers? So you should be more robust for alpha greater than 1. Are you robust to imbalances, where maybe alpha less than 1 works better? Okay, so we took the CFAR 10 data set. My theory is for logistic models, but we know in practice we could do CNN 8, which is 8 layers of CNN, followed by 2 feed-forward layers. And we compare alpha equals 1. We've done this for a lot of values just here in this table. I've put these out. And you can see that when I take this data set and I randomly flip labels, okay, symmetric, meaning you can either flip it as +1 or -1. So you randomly flip labels by up to 5% of the data, up to 25% of the data. You see that alpha equals 4 gives you better accuracy by a whole percent point. Trust me, in the adversarial and the noisy settings, people are fighting over 0.1%. So this is actually very, very comforting and very encouraging, right? Same CFAR data set. We took two. I think we took auto and truck, which look very similar, and we took dog and cat, which look very, very similar, and we imbalanced them, saying one of them is 500 and the other is 5,000. So it's about 9 and 91% of the data, okay? And if you look here, you get up to 3% improvement when you drop alpha for each one of these binary combination. We dropped all the others from CFAR, we just took these two, okay? All right, so in summary, we actually introduced a class of loss functions. We showed that they're classification calibrated. You can write them in a margin-based form. We use the theory of SLQC to, give you some notion of optimization landscape for the logistic models. We also actually argued, both in theory and practice, that you don't need to go, certainly alpha is a hyperparameter, but it doesn't need to be over a very large range. Right? We're looking at how to adaptively choose it. We can use Bayesian methods to do that. If you know something about the data, you can zoom in on which range to use. We want to generalize use these SLQC techniques to go beyond logistic models all the way to DNNs. And if you think about it, this is a logistic model, right? So if I stack it up vertically, I get a one hidden layer, and I could do that for multiple. And we have some results. Hopefully by the end of this month, we should have a journal on that. We're also looking at it in the boosting setting. We're also applying it to adversarial examples to see if this still holds up beyond just random noise. So, and that's where I'm going to leave it. Thank you so much.
Thank you so much, Lalita. And we'll take questions from the audience. I have a question to get started, maybe.
Okay.
So it's related to the earlier question on the class of loss functions. If you take these log loss and the 0-1 loss and so on, are there other interpolating families that are known, or is the alpha loss the only known family?
To the best of my knowledge, I don't. So in that sense, actually, if you think about norms, norms are a way to interpolate, right? So this is actually a norm on a distribution, which is exactly what the Renier measures operate on. So if you do classification based on distribution, this seems like a very, very applicable model. But you could also generalize this to loss functions that are based on distances, where also norms come into play. Mm-hmm. So that's really as much. This is a great question. So Wainwright and his colleagues and his collaborators have a paper on surrogate loss functions, which uses information theoretic measures to quantify them. But they describe those surrogate loss functions based on some other parameters, not through these norms and distributions and margins.
Mm-hmm. Thank you.
It seems very cute, to be very honest. I don't know the greater relationship, but yes, I wanted to come back to the point in my slide earlier. Just give me a second. So here it is. So in the leakage measure that I talked about, the loss function is both in the numerator and the denominator, because it tells you if you had no access to any release of a data, and if you had access to a release, which is X itself, if you knew the distribution of just X, but if you knew Y, which was released, and then you had to guess X, this ratio is how much you leaked. And I think we've talked about this before, but yeah. But now all I'm doing is I'm just pulling out just the numerator or the denominator as just in learning.
So So I have a follow-up question. Is there any other questions?
Yeah, I see another question, but why don't you finish, Ram, and then we can further. Okay.
Yeah, let's get Radha's question. I can talk to you offline.
What made you run into alpha loss function? Yeah, rather, it actually came from this work. So I'll tell you a very short, quick story. So mutual information was used for a long time to measure privacy leakage. And there was really no adversarial model precisely for mutual information. And then Alan Wagner and his collaborators, Ibrahim Isa and Sudeep Kamath, came up with this notion that they said, let's have a guessing adversary that does the best single one-shot guess. And they wrote it out in this form as a ratio. You guess with just the data, or you just guess with the distribution, and you guess with the release of the data. And there, alpha is actually infinity. And then this simplifies to, if you're taking a norm on the distribution, it depends on the maximum on the distribution. Right? So Oliver and I started looking at this, and we asked this question. My colleague Oliver Cosset at ASU, by the way, an amazing information theorist. We were like, this is so related to guessing, and you could do alpha guessing like we have, which is done in information theory. So could we somehow straddle? And that's how we came up with raising this probability to this power. And then the scale factor here gives you all the Renyi measures. So this is a great question. Can it be done with other loss functions? We just started talking to this learning theorist from UW, by the way, who's at UT Dallas, who graduated from Rishabh Iyer. And we're actually going to explore this for some other loss functions, but we haven't yet dived into it. Beyond that, I don't know if it can be generalized. I really don't. Sure.
I have a quick follow-up on the previous one. So if you look at this, it seems like if you had the optimal P y given x for all these alpha losses, right, and they all should ideally, if you were doing the expectation and doing ideal optimization, the 0-1 loss should be the same.
Correct. Correct? No, the loss will not be the same. The argument.
The maximizing argument is going to be the same, right? So
correct.
Therefore, exactly. If you just wanted to declare, a point estimate, then they
consistent. Yeah, so they're base consistent.
Correct. Right? But in practice, they perform differently. This is because of the optimization landscape. Is that what even when evaluated on the 0-1 loss? Right, so you're optimizing for your alpha loss function, but then you just calculate in your end experiments, for example, you calculate at the end your 0-1 loss, right?
Right.
And
right.
Yeah. So is it happening because of the interesting shapes that you have in the optimization landscape? Is that how to think about this?
I think I understood what you're saying. Yeah, it's a very good question. Yeah, there's a two-part question here, right? Ideally, if you hit on the optimal, assume for the Gaussian mixture, we could hit the optimal. If you hit the optimum for the Gaussian mixture, it shouldn't matter what alpha is what you're saying.
Exactly. If you're evaluating on the 0-1 loss, it shouldn't matter because the maximizing argument seems to be the same for the base optimal or the optimal alpha.
Right. And the reason you don't do that, I do think, has to do with practice. I don't quite believe that you will hit the optimal in the same way. I think that there in itself lies a problem. So therefore, actually tweaking alpha greater than 1 will allow you to get closer to that accuracy.
Okay.
Unfortunately, I think that is the only answer that makes sense to me.
Right.
Yeah. I remember asking my student this question too, but yes, that's Even with the Gaussian mixture, I suspect that can happen in practice, unless you used very, very, very large number of samples. But the other interesting thing is, if you had imbalances in your data to start off with, so all these convergence properties are distribution dependent, right?
Right.
So I think if you had imbalances and you could account for them by, otherwise you're making a lot of errors on the outliers.
If you go to your optimal claim on P y given X star, right? You have.
Yeah. Right here.
Are you assuming that the X is uniform or something to calculate this, or no?
No, you don't need to assume anything.
Okay.
You don't need to.
So therefore, even for class imbalance or anything, as long as you got the theoretical optimal, it shouldn't matter. But practically it matters. So that's very fascinating.
Correct. And practically, exactly. And spot on, correct. And in practice, if accuracy matters and you have noisy data, which you don't theoretically model, then it helps to move towards the accuracy part with alpha greater than 1. And if you have imbalanced data, it actually helps to boost the outliers. So you, I cannot prove this. This is sort of intuition that you somehow, it's a way of sampling from them.
Mm-hmm.
Get that actual underlying distribution precisely. Yeah. You raise a very valid question. Yeah. Great question.
There's a question by Sudipto. Maybe Sudipto, you can, if you have audio, you can ask.
Yeah.
So in slide 39, you had the result of convergence where f minus f star absolute value, how many iterations it takes to get close to epsilon. It seemed like it was order of 1 by epsilon square. So in SGD or accelerated gradient descent, we have like order 1 by square root epsilon and 1 by epsilon like that. So by using the alpha loss, are we gaining anything on the convergence results of, say, using SGD for these functions?
Again, a very good question. So one of the things we are converging towards in practice, so I'm going to answer this question a little bit more broadly than the specific way you asked me this. I think today you can take a deep neural network and throw it at any problem and train the, I don't know, the breath out of it or the oxygen out of it to do really, really well, right? And I think alpha loss perhaps can help you a little bit, but maybe you could do it with log loss itself. Where I think this could be useful, so I'll come back to your specific, where I think this could be useful is if you are limited on an edge device to a low capacity model. And that is where I see better gains for these kinds of models. So we haven't yet, so SGD is going to do better than NGD by definition, right? So our next thing was to actually go back and do SNGD. I don't think we can do SGD. It's somewhat hard to theoretically analyze. So I cannot speak to a specific convergence like this. I think you cannot get everything. If you want to improve your accuracy, it is possible that you may have this problem. But what we're seeing in practice, at least with, say, CNN2, 4, 8, and so on, with CFAR 10, you can dramatically improve, and it doesn't take that long in practice. In theory, I have to go back and look at these results to give you a very precise answer, and I will do that. But I cannot directly answer this question on, get 1 over epsilon squared relative to, So I think you were talking about this result, right? You said slide 31?
39, yeah, slide 39. So
right
maybe, yeah, so t greater than equal to something. There was some, towards the very end. I think I missed the slide number or something.
Yeah, I think you're talking about, you're talking about NGD, I think.
Yeah, something.
That's standard NGD, and I think SNGD does better than NGD too, right here.
Yes, exactly. This is the equation I'm talking about.
Right. So you should not look at it as just epsilon squared. Epsilon over kappa is what matters.
Okay.
Right? So, I mean, the point is to say that if I'm within this ball of radius about the optimal, I'm going to declare victory. If I increase alpha greater than 1, that ball is becoming smaller and smaller. So, and you're right, it goes down quadratically. And to go back and look at your question is, should we get similar? Okay. So I think the idea is different. It's actually good that SGD gets similar. The point of using alpha is to now say, okay, so with SGD, can I actually, so by the way, all our deep neural network results are with SGD. And I still get an improvement in accuracy. It's only because I can somehow use the fact that I have some noisy data, I have some imbalanced data, and I can tweak alpha to improve my accuracy. SGD gets similar. There are two parts of this: accuracy and there is convergence. So the argument here is, so SGD gets similar, that's actually great. The only worry for alpha is it going to be so much harder to converge if you tweaked it away from 1, for example? We all use 1 in practice. And in that sense, it's not, right? So I don't know what the epsilon is in SGD. I mean, you have to remember this is really about radius. Yeah, I guess.
We can have a discussion offline, I think. But yeah. I think let's thank the speaker for the great talk and all the patient answering of the questions.
Thank you for attending. Thank you.